Okay, moving forward, we will be doing the singularity functions. Okay, so before we proceed to the step response, we need to know the singularity functions. So these functions, the singularity functions, are actually for the switching. Okay, so we need to be able to understand the switching and how to apply it as a function. Okay, so this is the singularity functions. Singularity functions is also called switching functions. Okay, and they are very useful for circuit analysis. They serve as good approximations to the switching signals that arise in circuits with switching operations. Okay, so there are um, three mostly used singularity functions. These are the unit step, the unit impulse, and the unit ramp functions. Okay. The unit step function where we will start is what we will be mostly using for our topic. Okay. Unit step function, and it has this symbol U of t. Okay, for unit, U for unit function. And take note, these functions are functions of time, and they denote, so u of t is 0 for negative values of t and 1 for positive values of t. So it would mean that after the time value t, it will only have its value 1 after time t. Okay. So before the time t, 0 ang iyang value. So this is how the unit step looks like. Okay, it has this value u of t is equal to 0 for time less than 0 and 1 for time greater than 0. And if we plot it in a graph, this is what it looks like. It has 0 value before the time 0, and instantly by at that time 0, this becomes 1. Okay. And this signal or this function will go on forever. No, should it go? Will go on forever unless there's another signal or switching actions that will happen. Okay. So the unit step function is dimensionless and it is undefined at t equal to 0, where it changes abruptly from 0 to 1. Okay. So basically, just to give you a brief background of it so that you can understand it easily, okay, this is how it looks like in a circuit. For example, we have a voltage source, say it's 30 volts, and we are going to write U of t. So 30 U of t volts. So singularity functions class is how we convert switching into function. Okay. So you don't have to mention that you have switched at time 0 or at time 1 second. So you did a switching. So we can actually not state those switching actions. You can just use the singularity functions to relay the switching that happened. Okay. So this one would mean that you have 30 volts U of t. Okay. So t at greater than 0. So at time greater than 0, the value of our voltage will be, you can pause the video and think first. No? So what do you think will be the answer to this one? Okay, at time greater than 0, the answer will just look like this. Okay, at time greater than 0, you will have 30 volts. Okay, and then at time less than 0, what would your supply looks like? Your supply would look like a short. Okay, why is it a short? Because at u of t at time less than 0, u of t is equal to 0. So 30 times 0 is 0. That means you have 0 voltage. Okay. Okay. How about if we actually have this one we call, since u of t is 0 before t and 1 after t, how about we do like this? Negative t, u of negative t volts. Okay. So if you have 30 u of negative t, what does it looks like? T greater than 0. You can pause the video and think first. Okay. So 30 u of t, you will get the value of a short because this is a negative t. U of negative t doesn't work after time 0. Okay. And at t less than 0, you get 30, you 30 volts. So this is what it looks like. Okay. Okay, so the unit step function also doesn't really strictly start at 0, no. It can start at any time. Your switching can start at any time. Like there's a switch after 1 second, so that can possibly happen. So it says here that if the abrupt change occurs at t equal to 0, where t is greater than 0 instead of t equal to 0, it means your time is delayed. Okay, so you will get u of t minus to is equal to 0 at time less than to and 1 at time greater than to. See, what does it looks like? It looks like this. Okay, so instead of starting in 0, it started at to. So to siya nag-start. Okay. What happens if you have something like this? Let's try 10 u of t minus 1 second ampere. Okay, 10 u of t minus 1 amps. Okay, at t greater than 1 second. What does our supply looks like? Looks like this. We have 10. At t less than 1 second, we will get an open because it's current, okay, current source. So that's how. So let's move on. This one is for the delay, no? It's a delay. Okay, nag-start na siya after 1 second. But your graph will be starting in a naka-forward siya sa graph. So medyo libog siya, hunahon. But this is how it looks like. Okay. Then you can also have an abrupt change of course at t equal to 0 or t less than 0. It means advance. Okay. Wala pa kakaabot sa 0, nag-switching na ka. Okay, so this is how it looks like. And in terms kung naatay graph ay naatay circuit, nato 10 u of t plus 1 second. Let's look like at t uh, greater than 1 second, negative 1 second. you get 10 amps. At t greater less than -1 second, so you get an open circuit. Okay, this changes no if, for example, you put a negative right here. Let's say we have a negative. Then u of negative t plus 1 amp. So how does our circuit looks like? 10 u of negative t plus 1. So it's delayed. No, sorry, it's advanced by -1 second, but it's negative t. So that would mean t greater than -1 second. What does our supply looks like? Sorry, this one should be current. So our current will look like this. It's open after time 1 second, and at time less than 1 second would give us 10 amps. So that is how you do the unit step function, okay, with its delay and with its advanced uh, functions. Okay. So, medyo libog ni siya class, naka +1, that's advanced. But for the graph, it's a bit delayed in the graph, okay? Kung negative, ano mo ang ganito na value sa inyong seconds. Okay, so, next. So we can use the step function to represent an abrupt change in voltage or current. So that is what we did, you know, like changes that oh, like the changes that occur in the circuits of control systems and digital computers. Okay. So you can express it as like this, the same way that we did. So if we let t equal to 0, then V of t is simply the step voltage VO U of t. Okay, we will move on to the unit impulse function. Because the unit impulse function is actually just the derivative. Okay? So if you derive the unit step function, like this one, du of t over dt, you will get the impulse function. And what does it look like? Oh, what is it? So you get 0 at t less than 0 and 0 at t greater than 0, but you get an undefined at t equal to 0. So how does it look like in the plot? Okay, so this is how it looks like. This is an impulse by its name. So at 0, you get an impulse signal. And the signal is around the infinity. Okay? So impulse signal, although it may look like something weird, no? It's called delta t is 0 everywhere except at 0 where it is undefined. Okay, so impulse current and voltages occur in electric circuits as a result of switching operations or impulse sources. So this one, I think familiar mo, especially when you're plugging in your laptops. Okay, so you get that some spark, no, every time you plug in your laptop, you get a spark. Right? That can be like example of an impulse. Pulsive currents and voltages occur in electric circuits as a result of switching operations or impulsive sources. Although the unit impulse function is not physically realizable, just like ideal sources, ideal resistors, it is very useful mathematical tool. So the unit impulse may be regarded as an applied or resulting shock. It may be visualized as a very short duration pulse of unit area. This may be expressed mathematically as like this. Okay. So if we integrate the delta t within the limits of 0 minus to 0 plus, you get a value of 1. Okay. Now, you can also use this one to get an like a unit value, no? So you can multiply 10 delta t, you get 10 unit of, of an impulse around t equal to 0. And also, if you get a delayed response, like t minus 3, and multiply it by -4, you get this kind of signal. And if you multiply 5 to the delta t plus 2, which is an advanced signal around -2, you get this kind of signal. Okay. So next, for our singularity function is a ramp function. So this one is a linear function. Okay. It's a linear function where you get this one, it's r of t, r for ramp, and you get 0 for t less than 0, and t value for t greater than 0. So it's almost the same as unit step, but unit step, you get a constant value right here, diba? A constant value. But this one, you get a function, which is, it's it's a variable t. Okay. So with that, you get a linear function. So the unit ramp function is 0 for negative values of t and has a unit slope for positive values of t. So with that said, you get this one at t equal to 0. You have a value of t since it's 1t. So you get a value of 1 for time 1. Okay. So that's your linear function. So the unit ramp may also be delayed or advanced. Okay. So r at t minus to, you get advanced at to. Okay. And you also get delayed. Oh no, sorry. This one is delayed. And another one is advanced at this one. At negative to. Something that I would also like to note is that this singularity functions now is very useful for signal processing. So like for example, we have a unit step function, um, 1 u of t. Okay, 1 u of t would look like this. It's a different color. 1 u of t would look like this. And it would continue forever. Okay. But if you minus it, you subtract it with 1 u of t, okay, what happens? No. Um, okay, you subtract it with t minus 1. So after 1 second, you minus it with 1 u of t. So this becomes, you have 0 here, you have 1 here. So let's erase. So this one would get like this. And it would go down because you minus it and continue forever. So you can actually make a lot of singularity functions. For example, you have this one. So you can actually um, get a singularity function out from this kind of graph. So this one would be a ramp, and then this others would be a unit step and another ramp right here. So, okay, that's it for the introduction to singularity functions.